start the record. Let's finish cross product. So last time we defined what a cross product is. It's a vector that's perpendicular to the plane of two vectors u and v. So u cross v is itself a vector. And it's got a magnitude and then times some unit vector that's pointing in the right-hand rule direction. And so we looked at the right-hand rule with the cross product, and then we looked at the determinant formula for cross product. And that's the way I prefer you to do that on quizzes and exams. So hopefully you can. So we did some theorems, we did some problems, and we left off at the end of example 3. So let's take a look at cross products of the unit standard vectors with each other. Can you do that? Well, sure, why not? They're vectors in space, so you can take cross product of any vector in space. Legal. So is it true that I cross j gives you k? Now, there's a couple ways you can do this. You can do it the slow way. Like if I wanted to do it the slow way, I would go, okay, let's go I hat, j hat, k hat across the top. I has components 1, 0, 0. J has components 0, 1, 0. And if we use the 3 by 3 determinant method, so you block off the row and column that I hat lives in, and you've got those components right there. Block off the row and column that J lives in. You get that 2 by 2, and then block off the row and column that K hat lives in. Now, when you do the 2 by 2 determinants, remember major diagonal product, here we have 0 minus the minor diagonal. Oh, but that's 0 also. Okay, great. Minus major diagonal minus the minor diagonal. Oh, we got 0 again. Are they all 0? No. Here we have 1 minus 0. Okay, great. And then if I write this in component form, I have 0, 0, 1. Is that the same as K? So is this first thing true or false?
It's true.
It's true. Very good. Because 0, 0, 1 is indeed the component form for K hat. So the answer for I here is true. That's a true statement. Okay. You can test it with the right-hand rule. So if you go back to, a sketch here. Oh boy. So here's the X, here's the Y, here's the Z axes. Remember that I hat points in the positive x-axis direction, and J hat points in the positive y-axis direction. And if I take my fingers, here's my hand. Oh, that doesn't look too well. But if my fingers curve through the I hat first, then the J hat, and then I close my fist, my thumb will be pointed up in the positive z-axis direction, and it will be giving me K hat. So that's how you tell. Now, what about I hat cross K hat? Is that going to give you J hat? And it turns out this is also true. And you can kind of use your right-hand rule. If I were taking my fingers and I'm underneath here, the table, and I use my fingers to first go through I and then through J, and then close down my hand, I'm going to point in the, am I going to point in the J hat direction? No, that'll be false. Sorry, it's going to be negative. So how could I prove that's false? How can I prove I cross K is not J? I'll do it the slow way. I and then K. And then use your 3 by 3. So here you've got this 2 by 2 like this. I hat minus 2 by 2 J hat plus 2 by 2 K hat. Here I get 0 minus 0 I hat minus 1 minus 0 J hat plus 0 minus 0 K hat. So this looks like it's just going to give me negative J hat. Yep. It's going to give me negative, and this says positive, so it's definitely false. Okay. And then I'll let you try number 3. Number 3 actually is a true statement, and you can show it by doing the 3x3 determinant method.
Professor?
Yeah.
I don't understand how you know the values of I, J, and K.
Because when we define the unit standard vectors, that's what they are.
Oh, right.
So if you go back to your lecture notes in 13.2, when we actually define what I and J are and K in 3D, they are these unit vectors pointing in the positive X, Y, and Z axes. Do you remember? Maybe. I did. Okay. So let's talk about the triple scalar product, shall we? Also known as the box product. So if you have 3 vectors in space, the triple scalar product is known as the dot product of one of them with the cross product of the other 2. And it turns out this is a scalar, because remember, when you do a dot product of a vector with a vector, you will get a scalar. But what scalar do you get? And it turns out if you take the 3x3 determinant of all 3 of these vectors, so you put U components across the top, U1, U2, U3, and then V1, V2, V3 in row 2, and W1, W2, W3. And for you folks who already know about determinants, it turns out you can expand along any row or any column. I don't want to get into that. That's more of a linear algebra thing. So just do it the way I've been going over every time when we do the cross product. Go ahead and expand along row 1. So you're going to have a 2x2 multiplied with U1 minus a 2x2 determinant times U2 plus a 2x2 determinant times U3. And because what we're expanding along is the top row, which isn't IJK now, these are just pure numbers, you're going to be getting your final result as a pure, W2, as a pure number. And we'll do an example here in a couple of shakes. So what's the use of the box product? Like, can anybody use it for anything? Yeah, you can use it to find a volume of a box. And the box may not even be straight up and down. It might be sheared a little bit like this one, where all 3 of the vectors, U, V, and W, are adjacent edges of the box. Okay, and it turns out the volume, because you want it to be positive, will be the absolute value of this box product. You want to ensure that you get a positive result. Now, how come, why does this work? Like, well, just because I said so? No. That's not why. Let's not just buy it because the teacher said so. Let's walk through a quick derivation of why this works. So the volume of this box that's kind of angled a little bit is going to equal the area of the base. Well, what's the base? The base is this thing down here that's flat on the ground. Okay, I'm shading it in. That's the area of the base. And you're going to multiply that by the height of this box. And you have to be careful because the height is not the magnitude of U. Oh no. The height is found by dropping a perpendicular from the tip of U to the base. Here is the height. Oh my gosh, well, how do you get these? Let's do the easy part of this volume first. The easy factor, and I say easy relatively, is finding the area of the base down here. Because V and W make up adjacent sides of that base, and it is a parallelogram, we learned from last time that the area of a parallelogram can be found by taking the magnitude of the cross product. So boom, there's the area of the base. Yay. Now what? Well, how do we get this height? Very carefully. Well, what do you mean? So I'm going to use some of our knowledge of projections from last time. So you have to kind of imagine some things here. If I got V cross U, just say I did using the right-hand rule, V cross U or V cross W would be a vector, that's this vector here, that would be orthogonal to the base, essentially. Okay, fine. But what's that got to do with height? That's not helping me. Well, sure it is, because what we're going to do is we're going to project the U vector onto the cross product. And then this vector here, which is the projection of U onto the V cross W, we're going to take that guy's magnitude, and that'll be the height, because this magnitude is the height. So if I continue with my volume calculation here, so I still have volume equals, we still have area of the base, which is that area of the parallelogram, times, and we're going to take a magnitude of the projection of U onto V cross W. Now, let's use our knowledge of projections, which we did earlier this week. This is from the previous section, so this is really good review. By the way, this is just a multiply. This cross does not mean cross product. Okay, this means multiply this scalar with the other scalar. Okay, so how do we get this? So you're going to have magnitude here, but what is the projection of U onto V cross W? And if you remember, the vector that you're projecting onto something else shows up less frequently in the formula, the projection formula. So it's going to be a scalar times a vector. Which vector? Will it be U or V cross W that goes right here? Anybody want to gander a guess? I know some of you may not feel comfortable enough for that, but I claim it's going to be the one we're projecting onto, V cross W. And then the scalar has a dot product in the numerator, U dot product V cross W. And then the magnitude of V cross W squared. Now, because this vector has magnitude bars around it, you're taking a magnitude of that. The magnitude of this vector is just magnitude. What's magnitude of magnitude? Doesn't change anything, it's just itself. So I'm just going to copy it down. What's the magnitude of a dot product? It'll be the absolute value of the dot product. It'll force it to be positive. And then this magnitude is still there. So that hasn't gone anywhere. We're still going to have magnitude of V cross W. Fine. Now, what I'm going to do right now is I'm going to reduce this huge mess to lowest terms. Does everybody see that I can do some canceling?
Yeah, I mean, can't you just take out V cross W on the top? So you
Yeah,
just
V
have
cross W, and it's going to go with one of these V cross W's, but this V cross W goes with the other. So all the magnitude of V cross W's are gone. Boom, done. And what's the only thing that's left? Absolute value of the box product. Aha! And I'm done with my derivation. There we go. Happy face. And that's why it works. Because it works. And we have the volume of that box that looks like it's kind of sideways. So let's actually do a box product in this next example. Okay, so we're going to find a volume of the parallelepiped. That's the name of that shape that's got, looks like a box, but it's kind of pushed over a little bit, angular. You got U, you got V, you got W. Those are the adjacent edges. Fine. So the volume is the absolute value of the dot product of U with V cross W. Now, folks, you could do it this way. You could first find a cross product of V and W. Okay, and then take its dot product. Okay, and then do the absolute value. But the shortcut way, and I do claim this is a shortcut, is to use this 3x3 determinant method. It's quicker. You don't have as many steps. Well, this is hard, I think. Okay, well, I claim it's easier. So now you expand along row 1. So you're going to have a 2x2 determinant times 3 minus a 2x2 times -5 plus a 2x2 determinant times the 1. And then you fill in the blanks for those 2x2 by blocking off the appropriate row and column. And then the 2 by 2 determinants, you're going to do major diagonal minus the minor diagonal. Here you're going to have 0 minus the -6 times -5 plus. And there we have a 0 minus 6 times 1. And what do we have here? Okay, 2 minus a -2, that's 4 times 3. Minus this minus 6 is really +6. 6 times -5 is -30. And then plus a -6. But then we have 12 minus a -30 is really 12 plus 30. And plus a -6 is really -6. I get 36. And it is a volume, so I'm just going to put units cubed. They didn't give me the units, but it is a volume. I didn't have to take the absolute value of this answer. Why not? Because normally I would. Because it does represent a volume. But this final answer, when I did this 3 by 3 determinant, I was lucky and I didn't get a negative number. Sometimes you might. Just remember, if they're asking for the volume, go do one extra step and take that absolute value. That's example 4. Question: what can you conclude about the relationship between 3 vectors if their box product is 0? Oof. So the volume of the box is 0. What would you conclude? Well, this is a weird answer. It means that somebody squashed the box. Somebody stepped on the box. And so all the 3 vectors, u, v, and w, all lie in the same plane. So the volume would be 0, but here's what you can conclude, that all of the vectors lie in the same plane. And we call that coplanar. And I'll just put in parentheses, flattened box. All vectors lie in the same plane. That's what you can conclude if the box product is 0. That doesn't always happen. So how would you prove 3 vectors are coplanar? Show that the box product is equal to 0. And that's proof enough that the 3 vectors are coplanar and they all live in the same plane. How do you prove that 3 points are collinear? You just had a quiz with that. So one way to do it is is the way that I showed you when we were looking at this student's work, which they did a very nice job here. So one way to show collinear is to show that after forming vectors like A, B, B, C, or whatever, that one vector is a scalar multiple of the other, and then work it that way. That's one way, and that's totally legit. But there is one other way that I'm going to go over right now. The only thing is, I like this way in your quiz better than the way I'm about to show you. Why? Because the way in your quiz works for any dimension that you're in. 2D, 3D, 4D, 5D, 20 dimensions. We're not going to go to 20 dimensions in this course, but other courses you might. So what of it? So the other way, you're limited because they have to be vectors in 3D. Well, why? Because we're going to use a cross product. AB cross AC would equal the 0 vector. That's one way to prove that that vectors are parallel. And that was a theorem that we did last time. And if you forgot, let's scroll all the way back to when this happened, just to remind you. Ooh, we've done a lot. That was this one right here. Number 3 in the geometric properties of the cross product. If U cross V is the 0 vector, then you're guaranteed that those 2 vectors are scalar multiples. Means they're parallel. That's how you can tell if points are collinear. Okay, that's just an alternate way, but it only works in 3D, so it's limited. Okay, fine. Any questions so far? Example 5 is a challenge problem. I saw this problem a few years ago and I thought, wow, that's just so cool. I just got so excited. I thought I'd share it with you. And I hope you find it as fascinating as I do. What I love about it is it's like a puzzle. You kind of have to do stuff and know some of your theorems and formulas in order to finish out the problem. So that's the part of it that I love. It's multi-step. Okay. So if you're kind of a nerd, you're going to like this problem. If you're the kind of person who like, oh man, that seems complicated, I don't know, maybe you won't appreciate it as much, but I think it's cool. Here we go.
I have a question real quick. All right,
Sure.
so it's about the code.
So you're given that A dot B is square root of 3. You get this for free. Okay, that's like, you know, it's not like, oh, I got to go prove that. No. They're giving you that as a fact that you can use. Okay. And they're telling you that if you did take the cross product, they did it for you, you'd get this vector. Oh, that was very nice of them. Now, what they're not giving you are the component forms for the vectors A and B. Oh, no. But we don't even have to find those in this problem. Like, don't go off and try to find it because you're going to run into a brick wall. And you don't need to because they just want the angle between A and B. So if I were to draw a picture, you know, and this could be in 3D here. Let's say here's A and here's B, you know, and here, and they want to find the angle between those two guys. Now, if we did have component form, remember there is this really cool formula, cosine theta is equal to the dot product of the vectors divided by the product of their magnitudes. That's a fact, and you always want to keep your eyes on that fact because sometimes it'll help you. So this theorem is really important, but I'm going to rearrange this theorem. In fact, I'm going to use the alternate version of it. What do you mean? Solve this formula for the dot product, A dot B. That just means clear fractions. Okay, so I get that. Okay, so what? It's not helping. Well, we're going to use some of our knowledge of cross products and dot products to help us. And so there's a hint here, that formula there, which is here. And then this formula was from a previous lecture. So how will that help us? Well, good news. I can take the magnitude of A cross B because they did give me A cross B. So let's just go get that. That'll be an intermediate step. And knowing what I know about finding magnitudes, which is the square root of the sum of the squares. Okay. Oh, good deal. I got a nice perfect square. Oh, I don't always get that lucky when I do magnitudes. I usually have yucky radicals. Okay, so what do I have? I have the cross product's magnitude is 3, but that's supposed to equal sine theta times the product of the magnitudes. Okay, so I'll stop for a moment. For this formula here, I'm going to substitute square root of 3 in place of the dot product because they did give me that was nice of them. And then if I divide both sides by cos theta, I can definitely have this as a fact. So save this for later because it's going to help us. Well, that doesn't give me the answer. I know. we're not there yet. So now that I know the magnitude of the cross product, I'm going to use this formula here. Well, how am I going to use that formula? Let me just copy it down. What I'm going to do is I'm going to substitute for the left-hand side the number 3 because that has to be true. And then for this magnitude product here, product of the magnitudes A and B, when I was using that alternate version of the angle between two vectors, I can say that the product of the magnitudes is the same as this quotient. So I'm going to substitute right there. Ooh. Okay. So now what? You're going to use this mess right here to solve for theta. So first I'm going to divide both sides by square root of 3. So then I'll have 3 over square root of 3 is this quotient, sine over cos. But sine over cosine is tangent. So what I'm going to do is I'm going to take tan inverse of both sides. And on the right-hand side, well, that just boils down to theta. And then if you use your graphing calculator here, I think I get 60 degrees. Yay! And we're done. Now, because the dot product was positive, we can assume that the angle between is acute, so we don't run into having to add 180 degrees or anything. So we're guaranteed that this is an okay answer. Okay. That was a little bit tricky of a problem. Good news, I'm not going to put that one on a quiz or an exam. Okay, it was a little involved, but what I like about it is you had to use some serious knowledge of theorems of dot product and cross product just to do the one problem. And sometimes when you do a problem, you have to use all of your tools at your disposal to find a solution to your problem. And that's what math is about, and that's what engineering is about, right? And computer science. Let's do torque. Physics. So torque is the application of cross product. So let's say you want to loosen a bolt with a wrench. Okay, when you apply a force to the end of your wrench in the plane perpendicular to the bolt, the twisting power you get is dependent on 3 things: the magnitude or length of your wrench, and we're calling the vector that goes with your wrench here R. So you want the magnitude of that. The magnitude of the force you're applying. And one other thing, theta, the angle that the force makes with the wrench. And here's a little diagram for you. I'm filling all the blanks in for you. So I hope you're following with me. So those 3 ingredients come into play when you're doing torque. Now, torque, they use a really weird Greek letter, tau, not just a T, tau. I don't make this up. Tau is the cross product of the wrench vector, if you will, with your force vector. So you could take a cross product to find your torque. And typically they ask you for magnitudes of torques when they're doing a torque problem. So the magnitude of your torque is going, and I should put a T tau on your tau here, will be the magnitude of your cross product. But now using the theorem, that's equivalent to sine of the angle between the wrench and the force and the product of the magnitudes. Okay. And if your force is parallel to your wrench, you're not going to get anywhere. Like, you know, your sine theta is going to be 0. So you're going to have 0. So when is your torque maximized? Your torque is maximized when your force is applied in a direction that's orthogonal or perpendicular to your wrench. You'll get more oomph, more twisting power. And then hoping it is what you're hoping. So let's do a little physics problem here. Let's say you're trying to tighten a bolt. And the diagram here on the left, we have a force of 20 newtons, and we're applying it to some wrench that's attached to some bolt. And let's say you're applying the force at an angle of 60 degrees with your wrench. And your wrench is 0.15 meters long. Fine. So we're going to figure out the torque for that diagram, as opposed to this diagram. Got another torque situation. You're applying a force at an angle of 135 degrees. Whoops, sorry. 135 degrees. Your wrench is 1/4 of a meter long. and your force is still 20 newtons, which torque is larger? What's got more torque? So let's do the left side first. So if we use this magnitude of the torque as sine theta times the product of the magnitudes of the wrench and the force vector, here I'm going to have sine 60 degrees. My wrench is 0.15 meters. My force is 20 newtons. I think sine of 60 degrees is square root of 3/2. And you'll multiply that with 0.15 and 20. And Newton meters is the units. And I get approximately, if I do decimals, 2.6 Newton meters. Okay, there's a torque. How about the torque for the other diagram? Is that better or worse or what? So you're still going to use this torque formula here. Same torque. Only this time, you've got your angle of 135 degrees. And your wrench is 0.25 meters long. And you still have 20 newtons for your magnitude of your force. Fine. I get approximately 3.5. And by the way, the sine of 135 is square root of 2 over 2. 3.5 Newton meters. So which one's better? Which one's more torque? Left or right?
Right.
Yeah. More torque. More force. Okay. And we're officially done with section 13.4. Congratulations. You now know everything you need to know about the cross product. Yay.
Oh, one last question about this. So is there any major factors that cause it to have more torque? Like, is there something specific, like more the angle or anything like that? The force?
Well, first of all, the longer your wrench, the better you are, right?
Mhm.
And the more force you apply, the better you are.
Okay.
Right? And then what maximizes your sine? If you look at your unit circle and you look at all the sine values you can possibly have, the maximum value for sine is what? Do you remember any trig?
1?
Yeah, which means your angle is what? When is sine a 1? Your angle is
Pi or 2 pi? No. It's pi, right? No, pi over
pi in
2.
it.
Pi over 2.
Pi over 2. Very
Yeah.
good. Perfect. Yeah, so if your angle is 90 degrees, your force with your wrench, you'll help maximize that torque. I like this meme because sometimes students think that they can let down their guard in Calc 3, but not a good idea.